Um, tomorrow we have a quiz. So the structure of tomorrow's day will start with our homework help hour, as will be typical. So from 8 to 9, you can come in and get homework help. That hour is optional. So show up if you want the help or want to hear me talk about some of the problems from homework, whether you did them or not. You can show up and just be an observer. You don't have to participate. You can just sit in the background and watch and maybe learn. Maybe get a different perspective on how to solve a certain problem. After that, we'll start class at 9, and we'll go pretty quickly into our quiz. I might make a few announcements or just drag my feet for a moment to make sure we're all ready to go. But then we'll take our quiz, and then after the quiz, we'll get into the lessons for tomorrow, the notes that follow, and then the rest will be just like today. We'll do notes, we'll take a break, we'll do more notes, we'll take a lunch break, and we'll do more notes, and then we'll wrap it up. Okay, so just to summarize, tomorrow we'll have our homework help hour from 8 to 9. It's optional, and then at 9-ish, a little after 9, we'll start our quiz. After that's over, we'll get into our notes for the day, and the rest will be, well, just like everything else. Questions, comments, concerns, feel free to let me know. Anything you ever learned in mathematics up until what we've covered basically yesterday will be on the quiz. One thing that probably irritates students of mine historically, yeah, we'll be out by 2. That's our end time. That shouldn't end. Shouldn't change. One thing about me that probably historically irritates most of my students is I don't become very specific about what's on a certain quiz or a test. The reason is anything is fair game in mathematics up to what you've learned. And if I tell you to focus on, topics A, B, and C, then that's all you really learn. And then topics D, E, and F, which may be relevant later on, don't get any attention. And when you need them, they're not as good as they should be. And so my philosophy is just to say it's all fair game. Sometimes I will be more specific depending on what's going on. For instance, if we didn't cover a topic very well, I might say this topic is not going to be a focus of this assessment because, reasons A, B, or C. I don't know. Could be many different things. But for the most part, anything that comes in, before a pre-calculus class is fair game, all the way up into the stuff that I was teaching you about yesterday. I know that's not a very satisfactory answer, but it's my answer. If there are any other questions, please feel free to ask. All right, let's get into some right triangles, which is why I got a meme about right triangles on there, kind of. Just thought it was something worth putting on there. All right, so we're going to talk about, specifically, we have some special right triangles that you should be familiar with. A couple of students arriving late. Welcome back. Those of you who are just joining us, I talked a little bit about tomorrow's quiz. You may want to watch the start of this video when I post it later to make sure you get, I didn't tell you anything that's groundbreaking, so you didn't miss much, or you can ask a friend. All right, so we have 2 special right triangles. We have a 30, 60, 90 right triangle that we got to talk about. It's a little redundant to say 30, 60, 90 right triangle because the 90 is the right angle. But it's a bad habit that I got, and I will continue to exploit or utilize that bad habit and be redundant by saying also 45, 45, 90 right triangle. So those are the 2. I want to develop where they come from, why the ratios of the side lengths are in the ratios that they are. and then talk about how we use those, especially when we don't have access to a calculator. And if you're going to be taking the AP Calculus exam next year, assuming we go back to a completely normal year on campus in person, and you take the on-campus in-person version of the test, then you won't have access to a calculator for the entire test. You'll have it for some of the test and not the entire test. And there are certain trig ratios and trig values that you need to be able to evaluate without the use of a calculator. A lot of teachers teach this in terms of values on the unit circle. You'll see as we get deeper into the course, I don't like that method because it requires more memorization than I feel is necessary, and it's better to understand. And so we're going to start building that understanding by understanding these special right triangles, seeing where they come from, how the values and ratios are created, and then how they're used to generate some values for trig functions. And then when we start to project those into other quadrants besides the first quadrant, you'll see how we get those values as well. All that will be developed over time. Let's start with the 30, 60, 90. The 30, 60, 90 right triangle comes from, and let's see if I can make this look good here, comes from an equilateral triangle. And so I'm going to use the triangle tool. So this triangle is equilateral, meaning all the sides are the same. Okay. Sorry. And if it's equilateral, it's also equiangular. So that means all of these angle measures are 60 degrees. That one's also 60 degrees. I'm just not going to put it in there at the moment because I'm going to add something to the picture that's going to disrupt the writing of that number. So I'll add the 60 later, but it's 60, as is obvious. I'm also going to name the lengths of the side length 2x. And this side length down here is also 2x because we're talking about an equilateral triangle. So all the sides are the same length. Again, I'm just not going to write it at the moment because I'm going to add something to the picture right now. All right, so what I'm going to add to the picture is a height, and I missed or something happened with that. All right, so we had the height there. That's supposed to be a height, which means it is perpendicular to the base. And when you add the height to this equilateral triangle, you're going to bisect the angle at the top. So this gives us two 30-degree angles, which is why I did not want to write the 60-degree up there earlier. But that height also bisects the opposite sides. It cuts it into two equal pieces so that each of these side lengths down here are now both x. You don't have to call each side length of the equilateral triangle 2x. I just do that to avoid fractions prematurely. Students tend to be a little more cautious around fractions, fearful of fractions, downright dreadful or hateful of fractions. So we try to avoid it at least a little bit. Now the height here, since we have a right triangle, we can find the height using the Pythagorean theorem. So we have h squared plus x squared has to be equal to the quantity 2x squared. And it's important to put parentheses around the 2x because you have to square the 2 and the x, not just the x. And if you don't put parentheses, then the square only applies to the x. So the parentheses are necessary to be mathematically correct. And so if you expand the right-hand side to get the 4x squared, and you subtract x squared from both sides, because we're solving for h, we're going to end up with 3x squared here. And then we go to take a square root, and we don't care about the negative right now. We'll deal with negative roots for certain things later. We get something that looks like this. Now, we're not going to resort to a calculator. We want exact values here, but there is a property of square roots that says I can separate this into a product of square roots. Let me show you the little mathematical representation of that. Is the square root of the product of a times b is equivalent to the square root of a times the square root of b. So I'm just applying that property of square roots to this example. The reason why I'm doing that is because the square root of x squared nicely cancels to give us x. So that means h is going to be x times the square root of 3. We tend to write the x first because we don't want to confuse people to reading that the x is, whether or not the x is under the square root. And there's ways to avoid that. And this is one of the ways that's typically done. So now we know that the height here is equal to x root 3. Now there's a way that you should hold this in your mind because you should memorize. Let me back up one second. I don't tell you guys to memorize everything in mathematics that we come across because one, it's nearly impossible, and two, understanding is better than memorization. But I do tell you guys to memorize some things because you don't want to have to recreate everything that happens in mathematics. Mathematicians often do recreate much instead of memorize. And so I encourage that a lot with my students. But there are certain things, especially when we're going to have a timed test to take. And if you get to AP Calculus, it is a timed test. You don't want to have to take the time to do all of this work that I just showed you to come up with the ratios of the sides of the 30, 60, 90 triangle. It's better to have it memorized because you're in the middle, you'll be in the middle of a timed test. So anyway, the way I hold this in my brain for this right triangle over here is, as we talked about earlier, the smallest angle of the triangle is opposite the shortest side. So 30 degrees, its opposite side, x, is the shortest side. The hypotenuse in any right triangle is always the longest side. Okay, and then the 60 degree, the side opposite the 60 degrees, this leg over here is in the middle. But I want to think about it differently. The two perpendicular sides of a right triangle are typically called the legs. And so the two legs, we have a short leg, x, and we have a long leg, the height in this case. And it's always the case that the long leg is equal to the short leg multiplied by the square root of 3. That's what it says right here. X is the short leg. Okay, you can see that x is sitting right there and it's being multiplied by the square root of 3. So the way I hold it in my brain is the long leg is the short leg times root 3, whatever the length of the short leg is. In this case, we're calling it x. So to go from the short leg to the long leg, I just multiply the short leg by the square root of 3. To go from the short leg to the hypotenuse, as it says there, I just double it. The hypotenuse is 2 times x, 2 times the short leg. So to create the missing pieces, if you have missing pieces for a 30, 60, 90 right triangle, in my head, I hold it as a reference to the short leg. To get the hypotenuse, I double the short leg. So if I know the hypotenuse, to go back to the short leg, I have to reverse multiplying by 2, which means I have to divide by 2. So I could do that. I could just divide by 2 to get from the hypotenuse to the short leg. Or to go from the long leg, actually, let me start over. From the short leg to the long leg, like I said, I would multiply by root 3. So if I was going in the opposite direction from the long leg back to the short leg, I would be dividing by the square root of 3. So that's how I hold it in my brain. So I don't typically draw the full triangle out. I just draw a 30, 60, 90 right triangle and label things correctly. Whoops, 30, 60. And then this is x because that's the short leg. This is x root 3 because that's the long leg. And this is 2x because it's the hypotenuse. Now, to be even more efficient than that, we tend to scale this down by a factor of x. What do I mean by that? These ratios hold by multiplying by a constant or dividing by a constant, because any triangle that's a 30, 60, 90 right triangle is going to be similar to this 30, 60, 90 right triangle. So if I want to draw it a little bit cleaner than that. If I draw a little smaller one here and it's still 30, 60, 90, you should have learned about similar triangles back in an earlier class. And we have an AA triangle similarity theorem that says if two triangles have two corresponding angles that are equal, then the two triangles are similar. And these do. So that means whatever side length this is right here, this is going to be in the same proportion. Then this has to be y root 3, and this has to be 2y. No matter what y is, I have to double it to get the hypotenuse. I have to multiply it by root 3 to get the long leg. But we try to simplify this as much as we can, and we just draw a more simplified version of this without any variable whatsoever. If I draw a 30, 60, 90 right triangle, like this, and I divide everything in this triangle by y, or I divide everything in this triangle by x, I end up with 1 for the short leg, root 3 for the long leg, and 2 for the hypotenuse. And this is the one that you should memorize. Because if you need to evaluate a trig function based on, or rather at one of these angle measures, 30 or 60, you could read it directly from this triangle. The x's or the y's or whatever scale factor we have reduces in the ratio anyway. So for instance, if I wanted the sine of 30 degrees from this triangle here, 30 degrees is this angle, the opposite side is x, the hypotenuse is 2x. And I can cancel those x's and get 1/2. If I went to this triangle over here, the sine of 30 degrees would be y divided by 2y, opposite over hypotenuse, which again reduces to 1/2. So why bother having those scale factors in there when I could just use a basic triangle like this and use the short leg rather to be 1, hypotenuse to be 2, and the long leg root 3. Opposite over hypotenuse is still 1/2. It's the same in any of these triangles with a little less work on the one on the right, because then you don't have to do the step of reducing the fraction. And the same thing is true if you wanted to do the cosine of the angle. Or let's do cosine of 30. Cosine of 30 is going to be adjacent root 3 over the hypotenuse 2. If I wanted tangent of 30, tangent is opposite over adjacent, so it's 1 divided by the square root of 3. And we could do the same thing for the 60-degree angle if we wanted to. I'm not going to work that one out for you. You can write out the ratios for sine, cosine, and tangent of 60 degrees for yourself if you want. They're just referenced from the 60-degree angle instead of the 30-degree angle. One side note, ladies and gentlemen, I don't know what your previous teacher did for you or taught you about leaving a square root in the denominator like this. A lot of teachers force their students to rationalize and not leave a square root in the denominator. I am not one of those teachers. I don't care if you leave a square root in the denominator. In fact, I will leave a square root in the denominator most of the time, because it really doesn't matter whether you do or you don't. If you had a teacher who said you cannot leave a square root in the denominator, then you were dealing with a teacher who didn't fully understand the mathematics of what they were talking about. Okay, there is nothing wrong with leaving a square root in the denominator. The issue is more of a historical one based on a device that used to be used before we had calculators for doing calculations. And if you want to hear the boring story, I'll tell it to you briefly. If you don't want to hear it, well, then tune me out for a moment, which most of you probably have already anyway. There's a device, and I have one somewhere in the room here that I just saw the other day, and I should have brought it out, but I didn't think about it. There's a device called a slide rule. A slide rule looks like a bit of a ruler, but it has some brackets on there, and the middle piece slides out. So it's a ruler that has sort of an extension on it, but it's not designed to be a ruler. It's designed to do calculations. It's a precursor to a modern calculator. In fact, it was actually used to help develop the first set of calculators and computers that were designed, and then it did away. It sealed its own demise, if you will. But the slide rule was something physical that had markings on it. It had a log scale and some other stuff on there, and students were trained to do calculations on this device, because you had to be trained. I had to read about how to use these things because it's not an inherent natural thing. But if you had to do division, if you had to divide 1 by the square root of 3 on a slide rule, that was very challenging to do, because the square root of 3 is a non-repeating, non-terminating decimal, and it becomes much more challenging to do that division when the divisor, the denominator, is the square root of 3, this non-repeating, non-terminating decimal. If you rationalize it and make the denominator 3, the division process on the slide rule becomes much easier. So students were trained to rewrite the fractions without square roots in the denominator so they can use this device properly, efficiently, accurately. We don't use that device anymore. It's not necessary to rationalize the denominator to make the fraction easier to deal with on a slide rule. But it's still part of the curriculum, because most people don't understand that that's not necessary anymore. They were never told why. They never thought about why. They just blindly said, okay, I'll do whatever my teacher says. I'm not that kind of person most of the time. I am some of the time, if I want to be honest. But so if you feel like rationalizing, go right ahead. If you don't want to rationalize, don't worry about it, because I'm probably not going to anyways. Now, there is a process called rationalizing that we will use to do some other manipulations at other times. This isn't one of them, okay? This isn't a necessary rationalizing occurrence. All right, off of that tangent, it's probably much more info than you cared to hear. Let's get to our other special right triangle, the 45, 45, 90 right triangle. So the 30, 60, 90 comes from an equilateral triangle. The 45, 45, 90 triangle comes from an equilateral rectangle, better known as a square. I don't really want it in that color. Any other color lets me change that. I'm gonna, but it doesn't let me change from a highlighter. So I'll do that one more time. You guys still with me? You falling asleep? You don't have to respond. I get cynical sometimes because, well, when I'm not in front of you, I can't tell if you're paying attention to me. Anyway, we take a square and we add in one of the diagonals of that square. So we connect opposite vertices. And by connecting opposite vertices, what we've done is we've divided the angle measure into 2 equal parts. We've bisected it. So this becomes 45 degrees, as does this one. And so we've constructed our 45, 45, 90 right triangle. And since we started with a square, the 2 legs were the same. And so we would call those X. And then we would do the Pythagorean theorem to find the hypotenuse. And so we would get x squared plus x squared is equal to c squared. And so c squared is equal to 2 times x squared. So c is the square root of 2 times x squared. Again, we don't want the negative, because in this context, having a negative hypotenuse doesn't help anything, doesn't make any sense necessarily. And so using that square root property as we did earlier, we get the hypotenuse as x times the square root of 2. Incidentally, let me give you a little preview of something here. The square root of x squared really isn't just x properly. And I feel a little bit, I just get this little irritation in the back of my neck, because I'm not telling you all of the mathematics that's going on here. So this is really the absolute value of x. But because we're making x a positive number from the start, then they do just cancel and just become x, because the absolute value of x, if x is positive, is just the same number anyways. But more technically, this is something that you should know in general, because if you input a negative number in here, then you don't get a negative output, you get a positive output. So that's why it's the absolute value. But that's neither here nor there. That's not the point of the lecture. Just a little side note that you should be, of a relationship that you should be familiar with. So drawing out the 45, 45, 90 right triangle. Two legs are the same because it comes with a square. The hypotenuse is that side length that from the square times the square root of 2. Of course, like I said before, and I won't recreate the entire discussion, we could factor out or divide by that factor of x. So we can just leave this in terms of pure numerical values, that scale. So if I divide by x, I get 1, 1 for the legs and root 2 for the hypotenuse. And that's what you should memorize as you're trying to keep in your head a device for evaluating trig functions at certain angles. So memorize this one. Now, if you wanted to evaluate some trig functions, the sine of 45 degrees, use either angle here. Opposite is 1, hypotenuse is root 2, so it's 1 divided by the square root of 2. And interestingly enough, perhaps, or maybe you don't care, maybe you're yawning and not paying attention, the cosine of 45 degrees is exactly the same. Why? Because the adjacent and the opposite legs are exactly the same in this case. The hypotenuse is always the same. So in the SOHCAHTOA, O and A are the same. So that means the sine and cosine are the same. Also perhaps interesting, or perhaps not, the tangent of 45 degrees is 1 because the opposite and adjacent legs are exactly the same. So you should memorize these special right triangles so that at some point in the future, when you don't have access to a calculator and you're asked to evaluate some trig functions at 45 or 30 or 60, you'll be able to do so. And we're going to expand that ability over time because we are going to look at the unit circle. We are going to project these triangles into different quadrants and use reference angles to find the value of other angles. And I'll give you all of the details behind it, but just not today because it's not part of today's lecture. We're not going to do any practice with the special right triangles. We're just going to move on to fractional exponents. I got 3 more topics that should go fairly quickly. I think we're going to be, I think we're doing pretty well on time. Let me put it that way. Fractional exponents. I hope you have some familiarity with fractional exponents. So if I have some number x raised to the power of a divided by b, that's my exponent, you should be able to interpret what that means exactly. But just in case you can't or don't remember or never have seen this, if we think about raising this expression to the power of b, what would we end up with? Well, we went over some exponent properties yesterday, and we said that if we're raising a power, x to some power to another power, then we're going to have to multiply those exponents together. So a over b times b, which means that the b's cancel, and I get x to the power of a. That's kind of interesting. So what is that telling me? Okay, well, let's look at a concrete example here. Again, I'm assuming that you guys know this, but there might be a few people who have forgotten or maybe have never seen this. And so I'm trying to develop this in a way that will make some sense. Let's suppose for a moment that I have x raised to the 3/2 power, and I end up squaring that. What does that mean? Well, as we just saw from this work up here, that means we're going to get x cubed. You might be thinking, so what? But something happened here that might explain what that 2 in the denominator of the exponent actually means. Because we have another context. If I have the square root of something and I square it, we should know that the square and the square root do cancel here, giving us x. So now I just squared x to the 3 halves and I got x cubed. So something canceled there. So there should have been a square root embedded in here somewhere. And in fact, there is, okay? So let's go back to this line one more time and just take a look at it. Now, if I have x to the 3 halves squared, and something canceled this 2 out over here to make this be a 3, there had to be a square root in there. So really, we should be thinking about this as the square root of x cubed squared. Because notice that the 3 over 2, the 2 is gone from the denominator also over here. Those things canceled, okay? These cancel, leaving me the x cubed. So this is telling me that the denominator being a 2 told me we were taking a square root. More generally, if we have x to the power of a over b, this is telling me that we're taking the bth root of x to the power of a. Or we can actually reverse this a little bit. We could be taking the bth root of x and raising that to the 8th power, to the power of a. So when you see a fractional exponent, the numerator of that fractional exponent is the power that you're raising x to, or it's the power that you're raising the bth root of x to. And the denominator of that fraction is the root that you're taking. You're either taking it of x to the power of a, x to the power of the numerator, or you're taking the bth root, that root of x, and then raising it to the 8th power, okay? So this is what we mean, this is how we interpret the meaning of a fractional exponent. The numerator is the power that we're raising an expression to, and the denominator is the root that we're taking. Notice up here, just real quick, that we don't write a square root with a 2. Typically, it's not wrong to put a 2 there. It's just not convention, so it kind of looks funny to me, but it's not wrong to put it. So, you know, the 1/2 power is a square root. We don't tend to put the 2 for the square root. We put it for the other roots, however. All right. I want you to do an example. I'm sorry, I'm just noticing a question here on the Desmos activity. I'm not sure. What would happen if the sign is at the denominator and the numerator at the top? Josh, I don't understand your question that you typed in. I'm gonna need some help. At the top, like 2 over sine 20. Are we talking about the going back to the law of sines examples, or are we talking about something else? Because with the special right triangles, the question to me seems a little, I think, out of place. Now, maybe I'm wrong. There's no difference in the results that we get. Sorry, ladies and gentlemen, a question came up. I'd like to help. So if I go back up here, so it looks like screen 4 was one that we were able to solve using the law of sines. So if I would have taken this relationship here and wrote it in its reciprocal form, 11 over the sine of 112 degrees equals a over the sine of 36 degrees. All right, no, computer's acting funny. I was trying to erase that. See, computer's acting funny. We would end up with the exact same result, because I'm going to end up multiplying, to solve for A, I'm going to end up multiplying both sides by the sine of 36 degrees. So that these cancel on this side. And so I'm going to end up with A is equal to 11 times the sine of 36 degrees over the sine of 112 degrees, which is exactly what we found down over here, just doing slightly different bit of algebra. So if you write it in its reciprocal form, just do the algebra in the same way that you did the algebras before. All right, I've opened up screen number 10. And I'm going to give you a problem. I'm going to give you a few problems. Whoops, what screen do I want to be on? This screen here. Sorry if that was a little jarring. I would like you to not use a calculator to come up with the answers to what I'm about to write. If you decide to use a calculator, I won't know, but who are you benefiting by quote unquote cheating in this example by using a calculator? You should be trying to think this through so that you understand the numbers and not just go get an answer through technology that doesn't have any meaning for you. Okay, so I want you to simplify. That's the instruction. Let me add without a calculator or Desmos or computer or a slide rule or an abacus or anything else that you might want to use. Just use your brain and your understanding of what I just taught you to try to come up with a simplified value of 81 raised to the power of 5/4. And we're going to do all this on screen 10. Part A is going to be 81 to the 5/4. Part B is going to be 256 to the power of 3/4. And then we'll do a part C, which would be 1,000 raised to the 2/3 power. Again, please do not use a calculator.
Mr. Does B say 2 out of 4 or 3 out of 4?
3/4 is the exponent right there.
Okay.
Thank you for clarifying. Yes, Josh, for number 1. Yeah, I'll accept that, Valeria. That's true. I agree with your letter A, or number 1, as you called it, Juan. Cyrus, I was hoping you'd simplify that. That's true. That's what it means. But I was hoping that you'd simplify it. Now, I'm not asking you to actually multiply 81 to the 5th power by hand or even with a calculator. But there's another way of thinking about it that you should. I should probably just help you guys out here in the interest of time. Let me help you with the first one because it'll help speed things up a little bit. Now, remember up here, I said we have two different ways of interpreting this. I gave you two things over here. I gave you this version and this version. The second version is typically the one that's a little bit faster if you're going to do some mental calculation because it deals with smaller numbers. The first one, I got to take 81 and raise it to the 5th power and then take a 4th root. That's a lot of mental math or even paper and pencil math that I have to do. But taking the 4th root of 81 and then raising that result to the 5th power is easier. Well, at least if you know power, you know, some powers of some small numbers. So I would take the root first to get smaller numbers to deal with and then raise it to the numerator power, if that makes any sense. The 4th root of 81 is 3, so this is 3 to the 5th power, and then it becomes 243. If you take 3 and raise it to the 5th power, that's something you should be able to do. Dare I say mentally? Good, Josh. So far, so good, Juliana. All right, we're not going to wait too much longer for this. The book will give you problems where they say you'll see a calculator icon next to it and a circle with a line around it with a line through it. So it's telling you not to use a calculator. And that's all of these types of things. Again, I take the 4th root of 256 first and then raise that to the 3rd power. Now, whether or not you know the 4th root of 256 might be an issue. I'm old, so I'm pretty good with numbers sometimes. And so it turns out to be 4. And so this is 4 cubed, which works out to be 64. So take a 4th root, you can take a square root and then take a square root again. And then I would take the cube root of 1,000 first and then square the result. What number times itself becomes 1,000? Well, that's 10. 10 times 10 times 10 is 1,000. So the cube root of 1,000 is 10. And so this is 10 squared, which happens to be 100. So now you have a better understanding, I hope, of fractional exponents. We'll deal with stuff, more stuff related to that later. We're going to move on. You have the answers? We're going to move on to the next topic. So the next topic is the idea about radian measure. I got a question for everyone, and I'd love for you to use the regular chat for this one. Please, let's get some responses in the chat to this question. Why are there 360 degrees in one rotation about a circle? If you don't want to type it in, you can actually unmute yourself. I'd be fine with hearing your voice. Why are there 360 degrees in one rotation, one revolution about a circle? Nobody?
Sir?
Yes.
So from what I can remember, a radian measure is hold on.
Real quick, that's not what I'm asking at the moment, though, Josh. That's you, Josh, that's talking, right?
Yeah, sorry.
Okay, that's okay. I didn't ask yet what a radian measure is. I asked, why do we have 360 degrees in one revolution about a circle? I appreciate you unmiking, I really do, but you're about to give me an answer that I'm not sure I'm ready for yet. So I wanted to make sure I clarified the question. Do you guys have no idea why there are 360 degrees in a circle? Because there are 365 days in a year? Wild guess. That's actually not a bad guess, Elias. Okay, I'll come back and reference that in a moment. I want to see what other people have to say. Is it because it's 4 times 90? Well, it happens to be 4 times 90. That's true, but you kind of have the cart before the horse if you have any idea what that reference means. The fact that a right angle is 90 degrees is because it's 1/4 of the 360, not the other way around. But it still has, so we still haven't answered the question yet. Why are there 360 degrees in one rotation around a circle?
Well, I know that if you're looking at a circle and you cut it in fours, each like angle or side is 90 degrees, and times that is 4. So that, I mean, times, yeah, so then that equals 360 degrees.
Yeah, but all you've done, both Mia and you there, Cyrus, have only shifted the question. Why is a right angle 90 degrees? Why would a right angle be 90 degrees? Is it going to be something the Greeks or some people came up with to explain a crazy philosophy or something? I wish it was that interesting. I really do. But if there is an interesting story related to that, I'm unaware of it. So the problem, I'm going to try to reiterate this because a lot of students get this confused. A lot of students, they switch from the 360 to the 90 because they think that one question answers the other. And unfortunately, it doesn't, okay? The fact that we have 360 degrees as one rotation around a circle and the fact that a right angle or 90 degrees are directly tied together. Because we said one thing is true, the other one follows to be true, whichever one you want to define as true. But there still doesn't tell us why we defined either of those things to be true. Why did we set the number of degrees around a circle in one rotation to be 360? Or if you want to ask it from the other direction, why is a right angle 90 degrees? If you go back to Euclid's Elements, the original documents from which we get all of our geometry from, he doesn't mention 90 degrees in there for a right angle. He just says right angle. There's no mention of 90 degrees in any of his discussion, okay? So it still leads to the unknown at the moment. Why are there 360 degrees in one revolution around a circle? See, here's the problem. And I don't fault you guys for this too much. You guys are literally our best students always. The students who come into pre-cal and try and do this class, you guys are excellent students. But sometimes the problem with being such a good student is you listen and agree too much without questioning why something's true. And so somewhere in your past, some teacher told you that there are 360 degrees in one rotation around a circle, and you, being such a good student, went, okay, great, now what? Without saying, well, why? Do you ever wonder why? Probably not. Most people don't, because most people like you are just, tell me what I need to do to be successful, and I'm going to go do it without wondering why it's true. Now, I want to go back to what I think it was Elias who mentioned something. Because there are 365 days in a year, we don't really, I'm going to address that issue. We don't really know why we have 360 degrees in a circle. So really the short answer to this is somebody made it up. Somebody a long time ago decided we're going to let there be 360 degrees in one rotation around a circle. Now, why did they choose the number 360? Possibly because it's closely related to the number of days it takes to make one revolution around the sun. Possibly because there are 365 days in a year. And maybe they had that backwards. I like the comment, Argentina. That's funny. I'm gonna adjust it. Math is made up, but that doesn't mean it's not real. Okay. All the stuff that we're teaching you is all the stuff that humans have made up to model the world around us. And we have given it the name mathematics. And why do we teach it to all of you? Because it works. Because we can use it to make predictions about the world. Because we can use it to make these devices that you guys love, you know, your cell phones, your radio, your music, your cars, everything else that you love. Okay, it works. What if God just wanted it to be 360? Well, that pushes the question to someplace else. Now, I don't even want to go there. I'm going to get in trouble with the religious aspect of it. There's another hypothesis. So one hypothesis where the 360 comes from is it's related to the calendar. Another hypothesis is it's related to what's called the, not hexadecimal, well, it's a base 60 number system used by the Babylonians. Believe it or not, we use a base 10 number system. We use the digits 0 through 9 to represent our numbers. That's 10 symbols, because we have 10 fingers probably, or we're not even certain about that. And we represent our numbers in what we call a base 10 number system. Computers started with a base 2, zeros and ones, or now they use hexadecimal, base 16. But back in ancient Babylonia, they used the base 60 number system, which we still use a remnant of today, believe it or not. Think about a clock. How many seconds are there in a minute? 60. How many minutes are in an hour? 60. This is a base 60. This is a remnant of that base 60 number system of chopping things up into 60 slices. So some people hypothesize that the 360 degrees was used because it's related to the Babylonian base 60. Now, 360 has a lot of factors to it, meaning you can divide it by a lot of numbers and still get a whole number result. And so some people hypothesize that 360 is a nice number for that, okay? But we really don't know why 360 is the number. So why is it 60 in the first place? Why did they choose base 60? I don't know the answer to that question either, but it was used in the past and still carried down through history, and it still has a place in what we do today. Okay, maybe it won't have a place in time calculation, 1,000 years from now. Maybe something will have evolved and changed and be different, and then the 60 seconds in a minute and 60 minutes in an hour thing will be abandoned for something else. Okay, but as of right now, that's the convention that we use. There's another system. If you have, like somebody mentioned earlier, I think it was Matt, maybe, he had a TI-30 calculator. If you have a calculator that you can change the angle measurement input on, and you know how to do that, most of those calculators have 3 choices. They don't just have degrees or radians. They have a third choice. Are you aware of the third choice? It's called gradians. It's like the word radian, but with a G in front. And in that system, which is primarily an English, British system, in that system, they don't assume 360 degrees in one revolution around a circle. The assumption there is 400 degrees in one revolution around a circle. So in that gradient system, a right angle is not 90 degrees. In the gradient system, a right angle is 1/4 of 400 or 100 degrees. So they decided to make up a different system because they didn't want to use the 360. They thought using 400 would be better. And then if you use 400 instead of 360, things change. For instance, the sum of the angles, the interior angles of a triangle would no longer be 180. They would be 200 if you made one revolution 400 instead of 360. It could be in El Salvador feathering chickens instead of learning this. That's funny. Is this a good thing or a bad thing, Argentina? I don't know if that's a compliment or you're longing to be somewhere else. Anyway, the point is, now I want to leave. The point is the 360 is a made up number, okay? And 400 in the gradient system is another made up number. And we deal with that. There's consequences to that. Mathematicians didn't want to deal with just a made up number as a way of measuring angles. They decided to do something else. And this is where the radian number system comes from. They wanted to come up with something that was more natural to a circle. Okay, so let's get a circle here. And I'll tell you what a radian is. So let's suppose the center is right here, and we draw a radius from the center to the edge, length r. Now, if I was to start to measure along the edge of this circle here until I got a length along the arc of r units, so if I go out over here, let's say it's about right here, and I'm just approximating, so that this length here is also the same as the radius. And then I take another radius and I didn't draw for me. I don't know what I did. I'm sorry, ladies and gentlemen, I seem to be having some sort of technical difficulty at the moment. My notes crashed, so give me a moment. All right, so I think my notes are back. If they're not, let me know because they seem back to me. So if we, again, mark along the edge, the arc length of that's the same as the radius, and then I connect another radius to the edge of this arc over here, this angle measure right over here between these two radii, that is 1 radian. So 1 radian, I made it a little bit short, but that's okay. 1 radian is the measure of the central angle needed to subtend an arc of length r, length of the radius. Okay, 1 radian. Think of this as 1 radius angle. Meaning you have an angle measure here that gives you a radius length along the arc. So this is what mathematicians wanted to do. They wanted to make something more natural to a circle. And what's more natural to a circle than its radius? So let's project its radius along the arc and let's measure the angle that's created by that, let's measure the angle that's created by that arc length of r, okay? Now we've kind of dealt with this a little bit already. How long is one trip around the circle? Not in how many degrees. What is the arc length for one full revolution around the circle? Well, one full revolution in arc length, we call that the circumference. And the circumference we know how to calculate is 2 times pi times the radius. But what is this telling us? This is telling us that we can stretch 2 pi radii around the outside of the circle to make one full revolution. There are 2 pi radii. If I was to repeat this process and stretch another radius to here and another radius to here and another radius over to here and so forth, I could stretch 2 pi. Now 2 pi is about 6.28 as a poor approximation for it. I can stretch a little bit more than 6 1/4 of these radii fully around the circle. So that means one revolution around the circle in radians is 2 pi. Because I can stretch 2 pi radii around the circle. That means one full revolution has to be 2 pi. That is why 2 pi is equal to 360 degrees. 360 degrees because it's that arbitrary amount that we were taught back in preschool or whenever you learned it, okay? The more natural measurement in radians would be 2 pi. And so if we want to transfer or translate back and forth between the two, then we have to recognize that 2 pi has to be equal to 360 degrees. Incidentally, this 1 radian that we have up here, 1 radian is about 57 degrees. It's a little bit more. I'm rounding crudely here, but I don't have it memorized. I just know it's about 57 degrees. And so just to give you a sense of the size of 1 radian. 1 radian is a lot bigger than 1 degree, okay? It takes 360 degrees to chop up a circle. That's a lot of degrees. It takes only a little more than 6 to chop it up in radians. And so a radian is much bigger than a degree. Okay, but it's more natural to the circle because of what I was just describing to you. Oh, I think there's a question. I hope I haven't been ignoring that question for too long. Are you starting to think about lunch or a little dessert after lunch here, Elias? Is that what's on your mind? I wouldn't blame you. All right. All right, you're in charge of bringing pie for everybody. All right. Now that was kind of a long story to get to the point of what we were talking about here for radians, but let's get into converting here, because the main thing is here we have to know how to convert back and forth between radians and degrees. So if you had to convert from degrees to radians, should we do this? You guys have probably done this a million times already. I don't know how much we have to work on this. Isabel, I wish pi is a natural Greek letter, not the food. I like it though. I like it. It's a fine story for now. Let's say we had to convert 120 degrees to radians. And we're not even going to put this into Desmos. Let's say we wanted to convert, let's go 1,080 degrees into radians. If you know how to do it, just go for it. If you don't remember, I'll explain it to you now. In fact, to explain it to you, I'm going to go back up here really quickly and say, if I was to take this equation and divide both sides by 2, I would get that pi is equal to 180. If I was to divide by 2 again, pi over 2 would be equal to 90. If I divide by 2 again, pi over 4 would be equal to 45. I mean, we could do all kinds of manipulations here, but the key relationship is this, that pi is equal to 180, and that's how we can convert. If you go over to whatever it is you're trying to convert, put it as a fraction, if it's not already as a fraction, and then multiply it by another fraction, where if you have whatever units you have in the numerator here, that's the unit you put in the denominator of the fraction next to it. So I have 120 degrees, so I'm going to put 180 degrees down over here in the denominator. So the degrees cancel, and pi is equivalent to 180. So I'll put pi in the numerator. And then just do the arithmetic. 60 goes into here 3 times. 60, no, I'm sorry, 2 times. Goes into the other one 3 times. And so this becomes 2 pi over 3. And then if we had to convert 1,080 degrees, put it over 1, multiply it by pi over 180. And really, you don't have to reduce anything. You could do this and say, that is correct. Reducing is for 7th graders to do. But I'm going to reduce anyways. Whoops, not 8, that's 18. And then you might recognize that 9 goes into the numerator 12 times. And then goes in there 2 times. Oh, then that's just 6 pi. Now, what if I want to convert in the other direction? You'll have to do some conversion in the homework. That's why I'm just running through some quick examples. But again, you probably have done this before. You should have in a previous class. All right, so if you had to convert, let's say 7 pi over 12 from radians to degrees. And let's say we had 11 pi over 6. Notice we don't have a symbol for radians like we do for degrees. We can write rad after it. We just tend not to. We consider it a unitless measurement. And so we don't tend to put anything with it. So by the way, if you're going to use degrees, you've got to put a degree symbol. If you don't put a degree symbol on a number, I'm assuming it's radians from the start. So if you want to talk about 90 degrees, but you just write 90 without the degree symbol, I think you're talking about 90 radians, even though you want to be talking about degrees. So if you want degrees, you got to put the degree symbol so I know what you're talking about. Anyway, we got a fraction, so we're going to multiply this by another fraction. In my numerator, this whole thing's in radians, so I'm going to put radians on the bottom, which is the pi part of it. I'll put degrees on top, which is the 180. And then, like I said, we would multiply, which means we can cancel these pi's out. And then 12 has to go into 180, right? So it goes in there once. And how many times does it go in there? 15 times, I think. And then 15 times 7 is 70 and 35, 105 degrees. If my mental calculations are off, just yell at me or something. Like I yell at you. And 2 o'clock is coming fast. I talked too much about history today. We have one more topic. We should be able to get through it with no problem, but I'm just not going to delay. I'm assuming you're doing this on your own, or at least copying it down so you can understand it or have a model for it later. The pi's will cancel here. 6 goes into 6 once, goes in there 30 times. 30 times 11 is 330. And then the pi's cancel, so it's 330 degrees. So if they ask you to convert, now you know how to convert. The last thing I need to do is introduce you to the unit circle. And I said this yesterday, ladies and gentlemen, a lot of what we're doing right now is just should be review for a lot of stuff you've seen before. We're going to take it to a deeper level over time. But today, yesterday, some other days, it will be, might be simple. All right, let's talk about the unit circle. All right. Whenever you see the word unit in front of something like that as an adjective, they're telling you something specific. They're telling you something has a length 1, okay? 1 unit. And so in this case, for the unit circle, we're talking about the circle with a radius of 1. And even more specific than that, we're talking about a circle of radius 1 centered at the origin. So let me get a circle here on the screen, or something that's somewhat circular. And I'm going to draw in the axes by hand. So this is a unit circle, and to denote it, we often put the, where the point hits the axes here. So that tells you that it's got a radius of 1. This up here is at 0, 1. This is at -1, 0. And this point down here is at 0, -1. Now, the unit circle is going to be, something we use quite a bit going forward, so we want to be comfortable with it. We have different quadrants in, the XY plane that we talk about. The positive quadrant, where the X is positive and the Y is positive, is called quadrant 1. And then the rest of the numbers go counterclockwise. So quadrant 2 is right here, quadrant 3 is here, and then quadrant 4 is over here. We're going to define these quadrants in terms of their angle measures really quickly. Okay, so quadrant 1 in degrees is between 0, and I'll just call the angle measure theta, 0 and 90 degrees. Notice I did not put the or equal to. We do not include the axes in the quadrants. So this is not 0 degrees is not in quadrant 1, okay? The angle measure has to be between 0 and 90 in degrees. Notice I didn't put a degree symbol here. That's the rare exception. 0 degrees and 0 radians are identical to each other. So it's not absolutely necessary, but I'll put it down to be consistent. Now 0 radians and pi/2 radians would be the angle measures that define the first quadrant when we're in the radian. When we are in radians. Quadrant 2, ladies and gentlemen, you should be trying to beat me to writing these down so that you can make sure you understand them. Write them down faster than I am. And then if you get it right, great. If you got it wrong, fix it and learn from your mistake. All right, this is from 90 degrees, less than theta, less than 180 degrees. That's the second quadrant. And then in radians, it's pi/2 less than theta, less than pi. Quadrant 3, where they're both coordinates in quadrant 3 are negative. So we're talking 180 degrees, less than theta, less than 270 degrees. Or we're talking pi less than theta, less than 3 pi/2. Quadrant 4, 270 degrees, less than theta, less than 360 degrees. And 3 pi/2 radians, less than theta, less than 2 pi radians. Now, we talk about angles in the XY plane along the unit circle, and angles in the XY plane have a standard position. Okay, so I want to talk about angles in standard position, but I need some space. Okay. Now, just as a side note, actually, I want to do a little geometry just briefly. I'm going to move this down over here. Hopefully you can still see it if you need it. If we're talking about some angle, okay, an angle has a vertex, and from that vertex, there are 2 rays that emanate out from it, okay? This is the basic definition of an angle. And if you start at one of those rays and rotate some amount to get to the other ray, that's your angle measure, okay? How much you have to rotate to go from one ray to the other. The ray that you start measuring from is called the initial side. And the ray it ends at is called the terminal side. Initial, it starts there, terminal, it ends, okay? In standard position on an angle in standard position on the XY plane, actually, let me label one more thing, that's called its vertex. The vertex of an angle in standard position is at the origin. The initial side is on the positive x-axis, and the terminal side is, well, someplace else, possibly, okay? So this is an angle in standard position, okay? Again, standard position, let's make a little list here. So first point, vertex at the origin. Initial side on the positive x-axis. And I'm not going to mention the terminal side because the terminal side could literally be anywhere. It could also be on the positive x-axis if you're rotating 0 or 360 degrees or, you know, whatever. Lots of different rotations will get you there. But I am going to mention two more things. Positive angles rotate counterclockwise. I hope you know what counterclockwise is. If not, you should ask. Negative angles rotate clockwise. So when we're talking about an angle in standard position, we're talking about an angle that has these properties. And the way we defined our quadrants is assuming this positive angles rotate counterclockwise and negative angles rotate clockwise. That's most of what I need to show you, but I know we have 8, 9 minutes left, whatever. I do want to practice a couple things real quick. Specifically, I want you to be able to tell me in what quadrant a certain angle lands. I'm pausing because I don't know if everybody's done copying what I've written. So I'm just trying to give people a chance to catch up because I wrote a lot quickly. All right, so the question is, in what quadrant does the angle terminate? And I'll give you an angle measure in just a moment. And the angle, of course, is in standard position. And so let's say we had 950 degrees. In what quadrant would that terminate? Now, obviously, we're going more than 360, so we're traveling around the circle more than once. I'm just pausing to let people copy, think, process. Nobody's asking any questions at the moment, which is fine. That just means I'm doing a brilliant job of explaining everything. I know. There I go again, not being able to censor myself. All right, so how would I think about this? In what quadrant does this terminate? Well, what I want to do is I want to figure out how many times does this thing make, let me rephrase that, how many full circle rotations does this have? In other words, how many times does 360 degrees go into this number? Well, 2 times 360 is 720. Another 360 on top of 720 is more than 1,000, 1,080 if you want to be precise. So we're going to make at least 2 full circle rotations on this. So one way to think about this is to subtract 720, 2 rotations from this, and then see what we have left. Well, if I subtract that, I'm going to get 230 degrees. So for 950 degrees, if I do a quick little sketch, 950 degrees is going to rotate, it's positive, so counterclockwise. It's going to do 1 full circle for 360, another first full circle for the 720. And then where's 230? Well, if I keep going, there's 90 more, there's 180 more, and then 230 is somewhere over here. So this is going to end up in the 3rd quadrant. I see a question or a comment. Thank you, Monique. Excellent. Quadrant 3, you are correct. Okay. So that's where 950 terminates. And then you could do that similarly. Let's jump to a radian measure. Where does 23 pi over 4 terminate? I call it letter E. That's hilarious. Did I call that one up there? Letter B. I get quadrant 4 as an answer. I'm going to give a good solid maybe. Don't want to tell you if you're right or wrong. I want us to wait for a moment and let people think. Ooh, we'll get another quadrant 4. Got another quadrant 4. Got a lot of people thinking it's quadrant 4. I hope you're all right. I'm going to give you a way of thinking about it. I don't know how all these people are coming up with quadrant 4 because I'm not seeing the work that they're doing. And I appreciate the responses. So there's no criticism at all. This is just me. For those of you who don't know how to come up with an answer, I want you to have some mode of or method of thinking about it. So this is what I'm going to do. I'm going to break this down into chunks. What do I mean by that? I'm going to have pi be a separate chunk factor here. I got more people with the 4th quadrant. I'm going to ask myself, how many times does 4 go into 23? Obviously, it goes in there 5 times. And then it's going to have some left over. It's got 3 left over. Okay. So it's really 5 3/4, or 5 plus 3/4. That's what 23/4 is. Just rewriting it sort of as a mixed number, but I'm putting it as a sum. Why am I doing that? Well, 5 pi plus 3/4 pi. Let's think about the rotations about the circle. What does 5 pi do? Well, it's an odd multiple of pi. 2 pi gets me 1 full circle. 4 pi gets me another full circle. The 5th pi puts me right here. So this is how I get to the 5 pi part. But I still have to rotate 3/4 pi more, okay? So rotating past there, this is the green part here, that's only pi over 2. Now you guys know pi 1/2 is smaller than 3/4, so I got to keep going. 3/4 is going to put me a little bit further. It doesn't get me all the way to here because that's a full pi. And so yes, this is going to terminate in the 4th quadrant. I hope that made sense. If it didn't, well, let's try another. We'll start this one. We might have time to finish it before the end of the clock. And if not, 2 o'clock rolls around before we're done. I'll say anybody who doesn't want to stay can go, and anybody who wants to stay can stay. But where does negative 82 pi over 3 terminate? I'll give you a moment to think about it before I jump in. Ooh, I got one answer coming in. I got a different answer. So I got people in disagreement with each other. I got a quadrant 2 answer and a quadrant 3 answer. I'll give you both a solid maybe. I'm going to get started because we're inside the last minute here. So I'm going to factor out the negative. I'm going to leave that out there. I'll put pi out over here. How many times does 3 go into 82? Well, 3 goes into 8 twice. With 2 left over, and then 22 goes in there 7 times with 1 left over. So I get 27 1/3. So I'm going to think about this as negative 27 pi plus pi over 3. And I'm keeping the negative separate because the negative just tells me in what direction to turn, which direction we're rotating. We're rotating counterclockwise. 27 pi, well, that's 13 full turns. Do I want to draw 13 full turns? 1, 2, 3. No, I don't want to keep doing that because that's just too many. It's 13 full turns plus a half turn. So the 27 pi is going to get me to here, okay, after turning a whole bunch of times. Sorry, I'm checking the chat. And then pi over 3 more. Pi over 3 is smaller than pi over 2. So yeah, it's going to put me right over here into the second quadrant. All right, ladies and gentlemen, it's 2 o'clock. If you don't want to stick around, you don't have to. If you want another one of these, another example, by all means, you could stay. Have a great day, ladies and gentlemen. Remember, quiz tomorrow. Homework help hour from 8 to 9. Quiz shortly after 9. Have a great day, everyone. Like I said, if you want to stick around, feel free to stick around. Thanks, Juan. You too. Bye, Monique. Have a great day. Bye, Isabel. Have a great day. Bye, Cyrus. You're welcome. Have a great day. Bye, Samaria. Have a great day. That's okay. Have a great day, Elizabeth. All right, looks like we still got 5 people here. I don't know if I'm counted in that, maybe 4 of you. I'm assuming you guys want another one to take a look at. So let's go letter D, and let's go negative. Let's go 47 pi over 6. Negative 47 pi over 6. In what quadrant does that terminate? Alexis, I'm glad you're still here. I got to get some info from you so that I can send it to our IT guys to get you an email address so you can join our Google Classroom and get everything. I have to send it to you separately for now, okay? And so I'm glad you said something. So I will email you the homework. In fact, while people are working on that, on this problem here, let me go see if I can do that really quickly. I just got to change some permissions on this. Let's see. Anyone with link, copy link. Alexis, if you're still here, let me put this in the chat. This right, whoops, hit the wrong button. Alexis, that's a link to the homework problems. Give me one more moment to get the to get a link for the document that you're supposed to share. I don't know if you'll be able to do this part of it, but I'm gonna. Sorry, I'm still processing my thoughts here, Alexis. Excuse me for sounding like a moron, not being able to finish a sentence. This document here, I did not give you editing access to, but when you open it, you'll be able to view it. It'll tell you which problems are for homework. You can make a copy of it, attach. In fact, no, you don't even have to do that. Just look at it for the homework problems and email your pictures of your work that you do. Email those to me directly. And then hopefully we'll get you within the next day or two, get you into the class. And then I just thought of an issue. I don't know if I can do a Desmos quiz tomorrow because I don't know how you're going to access it. I have an idea. I think I know how to handle that. It's a little bit cumbersome, but I think I can do it. Anyway, Alexis, you probably don't need to hear me reason through that. Did you get all this stuff, Alexis? Can you at least look at it? Well, I'm going to stop recording.